Hi, welcome back to AP Physics 1, Unit 6, period of simple harmonic motion. Okay, so in this video, we're going to look at the period of simple harmonic oscillators, right? So period, so recall that when we talk about simple harmonic motion, it's periodic, which means that it's going to be repetitive motion, right? So it repeats itself in equal time intervals. Again, my big example for those, right? School, you're sitting in class periods, the bell rings, you move to the next one. So that motion repeats itself after a set amount of time. And that's what periodic motion is. Now, the period, which is abbreviated T, capital T, is the amount of time to complete one oscillation. So for a spring, it would be out to a maximum displacement or maximum amplitude, back past the equilibrium point, right? And then back to the equilibrium. So the time it took to do this kind of motion would be one period, right? For a pendulum, I pull it back to this position, I release it, right? It goes out through equilibrium to the far extreme and then back, okay? And it ends up back in our initial position. So whatever your initial position is, it always has to return to it for it to be a complete cycle of motion. Okay. Now, the frequency of a simple harmonic oscillator is the number of there and back oscillations per second, right? So the way you think about period and frequency is that period is seconds per cycle. Frequency is cycles per second. So you can see right now that these two have a relationship. T is inversely proportional to F, okay? Or you can do it the other way. F is inversely proportional to T, which leads directly to the equation of F equals 1 over T or T equals 1 over F, right? So if I have, a 2-second period, my frequency is 0.5 hertz, okay? Period is measured in seconds. Frequency is measured in hertz, which kind of unofficially, right, has the unit of 1 over seconds. Okay, so if you see anything to do with hertz, it's 1 over seconds. Now, just like as I mentioned, they have an inverse relationship. And so, again, remember, there's two types of simple harmonic oscillators, the pendulum and the mass on a spring or the mass spring system. So the period of a pendulum is 2 pi square root of the length of the pendulum over G. So L is the length of the pendulum, G for here on Earth, 9.81 meters per second squared. For a mass spring system, T equals 2 pi square root of M over K, okay? Where M is the mass attached to the spring and K is that force constant or spring constant. Now, when it comes down to in the long run, if there is a free response question on the AP test centered around, especially lab type question, centered around the period, you're probably going to have to linearize the data. And so the easy way to do that, especially for a pendulum, would be T squared versus L. And then for a mass spring system would be T squared versus M. Okay, so your L would be on your X, T squared would be on your Y for the pendulum, and then your mass would be on the X, and your period squared would be on the Y axis, and these two will give you linearized data. Okay, now let's look at two examples. One again will center around the mass spring system. The other will center around the pendulum. So here we go. We have an object. So this could be a multiple choice question. You have an object of mass M oscillating, right, with a spring constant of K for an amplitude A, assuming air resistance in the mass of the spring to be negligible. Which of the following changes alone will cause the period of this oscillation to increase, right? And so for us to do that, let's look at the relationships that are established, right, between period and the other factors, right? So one is very easy. For case 2, there's no effect of the amplitude, right? So case 2 is out. Nowhere in the equation, right, do you see amplitude mentioned, right? Mass is how heavy the object is. K is how stiff the spring is. Doesn't talk about if I pull it down, 2 centimeters versus 9 centimeters versus 5 meters. Increasing the amplitude would have no effect on the period of oscillation. So now we're looking at the mass and the force constant. So if we look at the relationships, right, T is directly proportional to the square root of m, and T is directly proportional to 1 over the square root of k. So note that mass and period have an increase, right? Mass and period have a direct relationship, which means if I increase the mass, I increase the period. So that's a good answer. And then T and K, I don't know why I keep wanting to write increase. T and K would have an inverse relationship, right? Because if K goes up, T goes down. Okay, and then vice versa. K goes down, T will go up. Let me do those in different colors. So if K went down, T would go up. So let's look at the option. It says using a spring with greater K. So that's this scenario here, which means my period would go down, which means then that is not a valid answer. So in this case, if this is a multiple choice question, you're looking for the one that says case 1 only. All right, let's look at a problem involving a pendulum. So the cool thing about pendulums, because of the equation, we can confirm, right, or deny or not confirm the acceleration due to gravity on planets, okay? Because if you look at one of the factors, right, that is, one of the factors is acceleration due to gravity. But if we look at the relationships, so T is directly proportional to the root L, right, and T is inversely proportional to root G, okay? And so this is a direct relationship. So if I increase the length of the pendulum, I increase the time. And then and these are inverse, right, which means if I increase G, T will go down, and if G goes down, T will go up, all right? So in this question, we're trying to determine what is the gravity or acceleration due to gravity of a planet. So the main thing about this problem is solving for G, right? So the first thing you're going to want to do is square everything. So you end up with T squared equals 4 pi squared L over G. And then we pull a little switcheroo here, right? I'm just going to flip-flop those two. So G is going to be 4 pi squared L over T squared. Okay? And so now it gives me the length, gives me the period. Right, so now all I got to do is plug this information in. So 4 pi squared times length, 2 meters, divided by 2 seconds squared. All right, plug that into the calculator, and lo and behold, we get an answer of 19.7 meters per second squared. So we take this onto our planet, right? We get up there. We find that G has a value of 19.7 meters per second squared. Okay, so this is the end of this video, which means there's only one video left. Again, Unit 6 only has those two main topics of period of simple harmonic motion and energy of simple harmonic motion. So we're going to focus on the energy aspect.